All right, so in this video, we are going to look at the procedure for conducting a one sample hypothesis test of a population mean, okay? This is usually the first hypothesis test that students will learn in a statistics class. Just want to give you some information here on what we're reading here. It's a hypothesis test, and that means we're going to be dealing with the null and alternative hypotheses, and we're going to ultimately make a decision whether we should reject or do not reject the null hypothesis. It's a one sample test, which means that we are only going to gather data from one sample from a population, okay, as opposed to a two sample test or a three sample test. So we're only going to have one sample mean, we're only going to have one standard deviation, we're only going to have one sample size, and it's a test of the population mean. So we're not testing the population variance, we're not testing any other qualities about a population, we're strictly testing the mean of the population. And what that means is, in the hypotheses, the null and alternative hypotheses, we're going to see the symbol for the population mean, which is mu. So you're going to see mu. Mu is the population parameter that you're going to see in the hypothesis test because this is a test of a population mean, okay? All right, so let's go through the steps one at a time. There are 6 steps. All right, so you may need to pause this video to write down all these steps as I go, but step 1 is you're going to state the null and alternative hypotheses, and you're going to state whether the test is a left tail test, a right tail test, or a two tail test. Okay. Now we alluded to this in a previous video about this left tail, right tail, and two tail test. We'll get a little more information in this video. All right, suppose we're dealing with a left tail test. Well, let me show you what the hypotheses look like for a left tail test. So this is the null hypothesis, H sub O or H naught. And you can see here that the null hypothesis, which like we said in the previous video, this is the standard assumption. We're going to assume this is true in the absence of statistical support. And we said that a null hypothesis means no difference. Well, no different is sort of the same thing as equals. So what we're saying here is that the mean of our test population is no different. It's equal to 30, which, let's say that this was the example of the headache medicine. Let's say that what the company thinks is the alternative hypothesis. They think that the mean time that a headache goes away is less than 30 minutes. That's the alternative hypothesis. But the null hypothesis is that the mean amount of time that the headache goes away is equal to 30. It's no different than all the other medicines, and that's why we use the equal. So our null hypothesis is going to be that the population mean, mu, is equal to 30. But our alternative hypothesis is going to be that the mean time is less than 30. The people at the company, they suspect that the amount of time for the headache to go away is less than everybody else, that it's different than everybody else. In what way? That it's less than everybody else, and that's less than 30. Now, because we're using a less than symbol, okay, that's what makes this a left tail test. So this is the norm. If we were to look at a normal distribution curve, a bell-shaped curve, we know that the mean, which is where z equals 0, the mean is sort of the norm, okay? This is what's normal for everybody, okay? And we're saying that our number is significantly less than 30, okay? Well, significantly less than, if the mean goes here, though z equals 0, the mean would actually be 30, okay? So on the actual normal distribution curve, not the standard normal, the mean would be 30. And what we're saying is that it's significantly less than. Well, what's over here? Well, we call these the tails. This is the left tail of the normal distribution curve, and over here is the right tail. And where are we looking for less than 30? Well, we're looking for less than 30 over here in the left tail. That's what makes this a left tail test. is because we're looking for the answer to our statistics over here in the left tail, okay? And so we're going to say that the null hypothesis is mu is equal to 30. The alternative is mu is less than 30. And since it's a less than, that's what makes it a left tail test. All right, another possibility for the null and alternative hypothesis or hypotheses is the null hypothesis could be mu is equal to some number. The number that I'm putting here, it doesn't really matter. This could be a 0, it could be 100, it could be 1,000, it could be 2,543. We saw 30 here before. This number is irrelevant. Okay, what you're going to see is what's normal. What you're going to typically see in all of these hypotheses is this part, and then this number is just given somewhere within the question. Okay. But what we can have sometimes is that mu is equal to, but that the alternative is now mu is greater than. That's how this one is really different than the last one we just looked at. In this case, we're hypothesizing that the mean is larger than some number, where the null is that the mean is no different than that number. No different means equals. And since this is a greater than, if the mean is right here and we're going greater than, that's over here, and that is the right tail of the normal distribution curve. And that's why we call this a right tail test. And you'll typically choose this one. You'll say mu is greater than if the question says something like, is more than, or is larger than, or something like that, okay? So if you hear larger than, or more than, or greater than, you're going to do mu is greater than whatever number they give you in the question. And then lastly, if you see a phrase that says that the mean is different than, it doesn't say more than, it doesn't say less than, it just says different than, or maybe it says something like the mean is not some number, okay? Well, that's the same thing as different than, okay? And so that means not equals to. So your hypotheses are going to go like this. The null hypothesis is going to be that mu is equal to some number, in this case 0, but it can be anything, okay? So mu is equal to a number. Our null hypothesis is always mu is equal to a number. Then the alternative hypothesis would be that mu is not equal to that number. And how can it be not equal? Well, if this is the mean right here, we can be not equal to the left and we can be not equal to the right. So either direction would mean we're not equal. That means we can be not equal in the left tail and we can be not equal in the right tail. And that's what makes it a two-tail test. So if it doesn't say more than or less than, it just says something like different than or it's not equal to, then you're going to use the not equal to, and this is going to be a two-tail test. And that is how we do step 1. We're going to state the null and alternative hypotheses. There's 3 possibilities, and then we're going to identify the possibility as either the left tail possibility, the right tail possibility, or the two-tail possibility. All right, step 2 in a one sample hypothesis test is pretty simple compared to some other hypothesis tests. In step 2, we're going to identify mu. Now, mu is going to be whatever number is in the null hypothesis, okay? So this number 30, that would be the mu. So we would write down here, we would say mu is equal to 30, okay? But if it's this one, mu would be equal to 8. If it's this one, mu would be equal to 0, okay? So we're going to identify mu. Then we're going to identify the sample mean, which is usually given in the question. We're going to identify the population standard deviation, which is usually given in the question, and we're going to identify the sample size, which is usually given in the question. Then we're going to state the level of significance, which we call the alpha, and I'll try maybe and post a video. There's a lot to be said about alpha. I don't think we're going to dig too deep into what alpha means, but let's just say for the sake of argument, and you can write this down, that alpha represents the probability of making an error in your analysis. It represents the probability of making an error, of making an error in your analysis and decision, okay? Mainly the decision to reject the null hypothesis or not reject. Now, I really, again, there is so much I could say about it right now in terms of error. First of all, alpha is not the only kind of error. There's also beta error. Deciding on alpha error and beta error is a big deal in research, but this is an introductory statistics class. So all we're going to say is that alpha represents the probability of making an error. Do we want there to be a high probability of making an error, or do we want there to be a low probability? We want there to be a low probability. So we want alpha to be a small number. And that's why typically alpha winds up being something like 0.05 or 0.01 or 0.10, something reasonably small, because we don't want there to be a very large error in our analysis and in our decision making, okay? We call that alpha, we call it the level of significance. So a lot of times in the question, it'll say at the 0.05 level of significance. That just means that alpha is equal to 0.05. And then once you've identified the alpha, which is given to you, by the way, it's going to be given to you in the problem. The last thing you're going to do is you're going to identify the p-value rejection rule. Let me show you what that looks like. All right, very simply, the p-value rejection rule goes like this. You're going to say reject H sub O. You're going to reject the null hypothesis if the p-value, which we'll just say p, if p is less than whatever the alpha is. And here we're just going to put a number, which is the alpha. Okay, so what I'm going to do is I'm going to put in parentheses the alpha. So if the alpha is 0.05, you'll say reject H sub O if p is less than 0.05. Okay, it really is that simple. Let's look at step 3 now. All right, in step 3, we're going to identify the critical z value and state the z-score rejection rule. Let's get to this in just a minute. Let's leave the rejection rule alone for a minute. We want to identify what's called the critical value of z, okay? And we only want to do the critical value of z if it's a z-test. And in this case, we are doing a z-test for the one-sample hypothesis. You could do a one-sample hypothesis test using other techniques, but we're using the z-statistic, okay? So we're going to use, you can use tables to do this. In fact, many AP statistics classes, they require you to use the tables. And I've taught with the tables for many years, but I also teach sometimes with the NumWorks calculator, and you can also do it with Minitab and Excel. We're going to do it with the NumWorks calculator. In order to identify the critical z value, with the NumWorks calculator, what you have to do is you have to go to the NumWorks calculator, and then what you're going to do is you're going to go to the app that's called the distributions app, okay? Once you get into distributions, you're going to select the normal distribution, and then you're going to make sure that you select a mu of 0 and a standard deviation sigma of 1. This is the standard normal, and that's where we're getting the critical z value from. We're getting it from the standard normal distribution curve, okay? And then once we're in there, I'll show you what to do. All right, so here's the NumWorks calculator. We're going to go down to distributions, then we're going to hit OK. We're going to go down to normal, and we're going to arrow over. We're going to leave the mean as 0. We're going to leave sigma, standard deviation, as 1. We're going to come down to next. We're going to hit OK. All right, so now what we're going to do is we have a choice. We can either select, there's 3 choices here if we go over to the left. This, where the orange is on the left, that's the left tail option. Down here, where the right side is orange, that's the right tail option. And this one with where the middle is shaded, sometimes we can call this the two-tail option, or you can call it the confidence interval setting. This is what we use for confidence intervals, okay? But oftentimes, even for a two-tail test, I will use the right tail, but let's look at these one at a time. All right, so let's say it's really going to be different depending on which kind of test you're doing. If you're doing a left tail test, what you're going to do is in NumWorks, you're going to choose the left tail option in here in the normal distribution. Okay, you're going to choose the left tail option, and then what you're going to do is you are going to enter the value of alpha, okay, which, like I said, could be, it could be 0.01, or it could be 0.05, or it could be 0.025, or it could be 0.10. Whatever alpha is, you're going to put that number. So let's say it's 0.05. You're going to put that number in the far right box. Okay, let's see what that looks like. So in here, the top one here, this is the left tail option. We're going to hit OK. Then we're going to go over to the far right box over here, and we're going to type in 0.05. This is whatever the alpha is. That's what we're going to put in here, and then we're going to hit execute. And look, it's going to give us our critical Z value right here. So this is our critical Z value. Okay, so I'm gonna write here Z star is in the middle box. Okay, all right, and that's how we find the critical Z value when it's a left tail test. Now let's see what happens if it's a right tail test. All right, if it's a right tail test, you're going to select the right tail option, and then you're going to do exactly what you did with the left tail. You're going to enter whatever the alpha is, enter the alpha in the far right box, And then just like with the left tail test, the critical Z value, Z star, is in the middle box. Okay, I want to write that down, maybe pause and write that down. Let's go over here. So we're going to change this to the right tail. This is the right tail down here, so we're going to go down to the right tail, hit OK. And again, let's say that our alpha, pretend that our alpha is 0.01. So we'll put in 0.01, and then we'll press execute, and then here is our critical value, 2.326348. Okay, now let's look at the two-tail option. All right, for a two-tail test, you're going to select the right tail option, and I warned you that that might happen. And what you're going to do is, instead of in the far right box, instead of putting alpha, what you're going to do is you're going to divide alpha by 2, because it's a two-tail test. So oftentimes with a two-tail test, we either double numbers or we cut numbers in half. Okay, so we're going to put half of the error probability in the left tail and half of the probability in the right tail. So we're going to take whatever alpha is. Let's say that alpha is equal to 0.05. Well, alpha over 2 then is equal to 0.025. So we would come over here, and we already have the right tail test. So we can go in here and put in 0.025, and that, whoops, sorry about that, and then enter, and then 1.959964 is our critical Z value. But here's the thing, with a two-tail test, you actually have to do, so we're going to say that Z star is plus or minus. So we basically have two critical Z scores, okay? One of them is the positive version, one of them is negative. So we're going to get this number, 1.959, and then 964, which, by the way, is basically 1.96. It's approximately equal to plus or minus 1.96. This is the most famous of all the Z scores in statistics. So here's what I want you to understand, is that our critical Z value is positive 1.959964, and also there's a second one, it's negative 1.95964. The reason we have a positive 1 and a negative 1 is because it's a two-tail test, okay? And that's it for step 3, identifying the critical z-value. And I almost forgot the last part here, the z-score rejection rule. So what we're going to write after we identify the critical value is we're going to say reject H sub O if, we're going to write this letter but without the star, if z, because that's the test statistic that we'll calculate in step 4. The absolute value of z is greater than the absolute value of z critical. Okay, so what we're going to do is we're going to take the positive version of z and the positive version of the critical value, and we're going to use the greater than. So if the positive z is greater than the positive critical value, then we reject the null hypothesis. All right, so now we'll move on to step 4, which we already learned how to do. We did this in the previous lesson videos. And you can look back at the separate video. It says calculate the standard error and the z statistic. Now we did the z statistic in the previous video, but let's talk about the standard error, okay? So we know that the z statistic can be calculated as x bar minus mu over sigma divided by the square root of n. We learned how to do that in a previous video. Notice all this information is already in step 2. We have the mu, the x bar, the sigma, and the n. So this is not going to be a problem. But let's go ahead and see how do we calculate the standard error. The standard error is easy. That's this right here. That's the standard error. So the standard error is just sigma divided by the square root of n. And this is going to be useful in step 6. So that's why we want to calculate the standard error. Also, if you already know the standard error, it's actually now easier to calculate the z statistic, or the test statistic, because we can do x bar minus mu divided by the standard error that we already know, okay? So that is step 4, calculating the standard error, which is this, and calculating the z test statistic, which is this. And now step 5. We identify the p-value, which we already learned how to do in a previous video. There was one video in the previous set of lessons where we calculated the test statistic, and then the next video right after that, we learned how to identify the p-value. So I'm not going to go over that right now. But then what you're going to do is once you have the p-value, you're going to compare the p-value to the alpha to determine whether you should reject or do not reject the null hypothesis. And then there's another comparison you're going to make. You're going to compare the z-test statistic from step 4 to the z-star, the critical z statistic from test 3, and decide whether to do not reject or to reject the null hypothesis. And here's how it goes. If your p-value is less than your alpha, then you reject the null hypothesis, and you're going to just write reject H sub O. But if P is not less than alpha, then you're going to say do not reject H sub O. And then the other way to do it is if the Z statistic from step 4, if it is greater than, and we already talked about this, if the, well, we're going to say if the absolute value of the Z statistic is greater than the absolute value of the critical Z statistic, okay, let's try that again. There we go. So if the absolute value of the Z statistic from step 4 is greater than the absolute value of the critical value Z statistic from step 3, then you reject the null hypothesis. But if the absolute value of Z is not greater than the absolute value of the critical value, then you do not reject the null hypothesis. We're going to do some examples in the next video of this. All right, step 6, the last thing you're going to do is you're going to confirm your decision, reject or do not reject. You're going to confirm that using a confidence interval. Now the confidence interval is really easy when you've already done all these steps, because what you're going to do is you're going to put should recall from a confidence interval, you're going to put these less than or equal to symbols, this one and this one, around. You're going to put mu in the middle, And then on the left here, you're just going to take x bar from step 2, x bar, and you're going to subtract z star, the critical z value from step 3, times the standard error from step 4. So we multiply z star times standard error, we subtract that number from x bar, and that gives us the number on the left. We do the exact same thing on the right, only we add. Okay, so we're going to have a number here, then a number here, and we're going to have what you actually see here. You're going to have less than mu or equal to mu, less than or equal to, okay? And here's what you're looking for. You want to see if mu from step 2, because step 2, remember, you have mu is equal to something like 30 or 8 or 0 or 100. If mu is on the interval from here to here, if mu is on the interval, then do not reject. Do not reject H sub O. But if mu is not on the interval, then you reject H sub O. If mu is not on the interval, so like if mu is 8, and this number over here is like 8.5, and this number over here is 9.7, 8 is not on this interval, and therefore we would reject H sub O. We're going to do some examples with this. It's probably a little confusing. Just make sure you've written down all the procedures. Make sure you've written down all these statements and the notes I've made. And now, in the next video, we're going to do some examples, probably about maybe 2 examples.